Analysis design of algorithm for RGPV exam Unit 1B notes are in comments section. Introduction to divide and conquer technique. 1. Definition. Divide and conquer is a problem-solving technique that involves breaking a problem into smaller sub-problems, solving them independently, and then combining the solutions to solve the original problem. 2. Steps in divide and conquer. A. Divide. Break the problem into smaller, more manageable sub-problems. B. Conquer. Solve the sub-problems recursively. If the sub-problems are small enough, solve them directly. C. Combine. Combine the solutions of the sub-problems to obtain the solution for the original problem. 3. Examples. A. Binary search. Divide the array into two halves, and recursively search in the appropriate half based on the key value. B. Merge sort. Divide the array into two halves, recursively sort each half, and then merge the sorted halves. C. Quick sort. Divide the array into two partitions based on a pivot, recursively sort the partitions, and then combine them. 4. Benefits of divide and conquer. A. Breaks down complex problems into simpler sub-problems, making them easier to solve. B. Allows for parallelism and efficient utilization of computational resources. C. Can lead to efficient algorithms with improved time and space complexity. The divide and conquer technique is a powerful problem-solving approach that can be applied to various problems. When designing and analyzing algorithms based on this technique, the following aspects should be considered. 1. Problem analysis. Understand the problem requirements and constraints. Identify the key components and characteristics of the problem. Determine if the problem can be divided into smaller sub-problems that can be independently solved. 2. Algorithm design. Divide. Determine how to divide the problem into smaller sub-problems. Conquer. Design the algorithm to solve each sub-problem independently. Combine. Define the approach to combine the solutions of the sub-problems to obtain the final solution. 3. Correctness analysis. Prove the correctness of the algorithm by using mathematical induction, loop invariants, or other appropriate techniques. Verify that the algorithm produces the correct output for all possible inputs. Validate the algorithm against known test cases and edge cases. 4. Time complexity analysis. Determine the time complexity of the algorithm in terms of the input size. Analyze the time complexity of the recursive calls and the combining step. Express the time complexity using big O notation and compare it with other algorithms. 5. Space complexity analysis. Analyze the space complexity of the algorithm in terms of the memory required. Consider the space used by recursive calls, auxiliary data structures, and variables. Express the space complexity using big O notation and compare it with other algorithms. 6. Comparisons with other algorithms. Compare the algorithm based on the divide and conquer technique with other algorithms solving the same problem. Consider factors such as time complexity, space complexity, simplicity, and practical performance. Evaluate the advantages and disadvantages of each algorithm in terms of efficiency, scalability, and ease of implementation. 7. Practical considerations. Consider practical implications such as implementation complexity, code readability, and maintainability. Evaluate the trade-offs between efficiency and practicality. Assess the suitability of the algorithm for the specific problem and its applicability in real-world scenarios. By analyzing, designing, and comparing algorithms based on the divide and conquer technique, you can gain insights into their efficiency, effectiveness, and suitability for different problem domains. It is essential to consider the problem characteristics, complexity analysis, and practical considerations when selecting and evaluating algorithms. 1. Binary search. Problem. Given a sorted array of elements and a target value, find the index of the target value in the array, or determine if it doesn't exist. Algorithm. A. Divide. Compare the target value with the middle element of the array. B. Conquer. If the middle element is the target value, return its index. Otherwise, recursively search in the left or right half of the array based on the comparison result. C. Combine. Return the index of the target value or indicate that it doesn't exist. Time complexity, O, log n. Each comparison reduces the search space by half. Space complexity, O, 1. No additional space is required. 2. Merge sort. Problem. Sort an array of elements in ascending or descending order. Algorithm. A. Divide. Divide the array into two halves. B. Conquer. Recursively sort each half using merge sort. C. Combine. Merge the sorted halves to obtain the final sorted array. Time complexity, O, n log n. Each division and merging operation takes linear time. Space complexity, O, n. Additional space is required for merging the subarrays. 3. Quick sort. Problem. Sort an array of elements in ascending or descending order. Algorithm. A. Divide. Choose a pivot element and partition the array such that elements smaller than the pivot are on the left, and elements greater are on the right. B. Conquer. Recursively apply quicksort to the subarrays on the left and right of the pivot. C. Combine. No explicit combining step is required. Time complexity, O, n log n. Average case, O, n squared. Worst case, when the pivot selection is not optimal. Space complexity, O, log n. For the recursive call stack. 4. Strassen's matrix multiplication. Problem. Multiply two matrices to obtain their product. Algorithm. A. Divide. Divide each input matrix into four equally sized submatrices. B. Conquer. Recursively compute the products of the submatrices using Strassen's matrix multiplication. C. Combine. Combine the submatrix products to obtain the final product matrix. Time complexity, O, n caret log 2, 7. Strassen's algorithm has a lower time complexity than the traditional matrix multiplication algorithm, O, n cube. Space complexity, O, n caret log 2, 7. Additional space is required for intermediate matrix operations. These examples demonstrate the application of the divide and conquer technique in various algorithms. Each algorithm follows the divide, conquer, and combine steps, but their specific implementations and complexity characteristics vary. It is important to analyze and compare the efficiency and practicality of these algorithms in specific scenarios.